a compromise between the accuracy and so this is more specific to triangles. So there's some common aspects. The one thing, maybe it's not obvious for people outside of the WaveWatch development. So the code for running on triangles and the code for running on squares or curvilinear grids is exactly the same. And the reason for that is that the mapping in space and the way it's done in the memory of WaveWatch, the space is handled as like one big vector. And so we have some, the structure of the grid is actually done by some mapping array, so it doesn't change the structure of the data in the memory. But of course, the numerical schemes are different. We need you have a special advection routine for triangles and another one for the squares, of course, because the geometry is a bit different. So there's a bit of repeat from what I had before. So so we're solving this wave action equation with the source terms. The typical idea is that you get some input of energy coming from the wind, which is giving some energy here in the middle. Some of that energy is transferred towards low frequencies by these nonlinear interactions, these arrows here, triad and quadruped wave interactions. And then you have dissipation, loss of energy at high frequencies in particular. All right, so yeah, you can skip this. So we're solving this guy with the left-hand side and the right-hand side. And so the different so the splitting of this equation is to integrate these different pieces separately. And so you have different speeds for each of these terms. So this is the advection speed in space, so the group speed plus the current that's moving the stuff in space. This is a change in the wave number, the change in the angle, which is a function, so the speed of change of the angle, which is a function of the slope of the bottom, and the shear of the current. I'm going to skip that one and go here. All right, so there's just to give you the big difference between SWAN and all the other models is that actually SWAN doesn't do the splitting, it's solving the full equation, all the terms together at the same time. The other models like WAM, WaveWatch, and TOMAWAC, for example, have chosen another approach, which is to solve different bits and pieces. So typically the first step is to solve that equation without the source term. So we integrate that with the time step delta t. And after we have done that, we integrate the source term with the same time step delta t. And if delta t goes to 0, you can prove that you get the same solution. Of course, you never use delta t equals 0. And you always introduce an error, which is called the splitting error, when you do the splitting, because it's not exactly the same to solve this and then that than to solve everything at the same time. The idea of using the splitting method is that hopefully the splitting error is going to be less than the numerical error that you would that you have if you actually integrate everything at the same time. And so that would be a first, so this splitting is typically done in TOMAWAC because there's integrating the spatial and the refraction at the same time using ray trajectories. In WAM or WaveWatch, there's another splitting level between the spectral advection, so the turning of the waves, and the spatial advection. So we actually have 3 steps of the equations. So we first, we first do that, then we do this, and at the last piece of the code we do that. If you are curious and you want to know where this is happening, this is happening in a module called W3 Wave MD, and you will see that this afternoon. And so W3 Wave MD does these 3 pieces, and it's calling different routine that does each of these parts. And the source term is integrated in a module called WSRCE MD. Right. And what is this one? Just same story. So now what is special about the triangles? So a few aspects about that is that instead of using finite differences, it's using residual distribution schemes. And the idea of that is you define a control volume, which is this gray area around each node of your grid. So the source terms and the spectra are evaluated on the nodes of the triangles. And so we need to compute the flux of energy going into this area. And based on this flux of energy, we will change this value in time. And there's different categories of schemes from low order to high order. So the lowest order scheme is called the narrow stencil scheme, the N scheme from TIC from 2002. And there's some other high order schemes that are available in WaveWatch. So in practice, for our coastal applications, we use a lot this N scheme. It's a bit more diffusive, but it's cheaper. And compared to the measurements, it's actually, from our results, it was actually usually more accurate. And Aaron hates this because he spent a lot of time developing the high order schemes and making them work. But the low order, in our experience, was actually faster and more accurate. And so you essentially express the wave action at the next time level as a function of the wave action at the current time level, and then this change in the fluctuation scheme. I'm going to skip all the details. If you want the details, it's all written pretty clearly in the thesis of Aaron Roland from University of Darmstadt. There's two important constraints on these advection schemes, whether squares or triangles or whatever. One is the Godunov theorem, which tells you that a linear scheme, meaning that the solution is a linear combination of the unknown variables, cannot be monotone and higher order than the first order. So in other words, if you want to have a monotone scheme which is linear, it has to be first order. The difficulty is, so why linear? Well, actually, it's very much easier to solve a linear set of equation. If you have a nonlinear set of equation, especially when you're solving all the terms together, you have you can write this as a huge matrix, and inverting that matrix to get a solution can be pretty nasty. That's so if you don't care about nonlinearity and have a complex problem, that's okay. The monotone issue, it means that it's not introducing other extrema in your solution. So if you have something which is smooth, it's going to stay smooth, basically. And one side effect of non-monotone schemes is that they can produce negative values, which for the energy is a bit problematic, like the temperature or the salinity also. So one difficulty is, either you have a first-order scheme which is very diffusive, and then it can be linear and monotone, or you try to do something high order, but then you have to face the problem of having spurious gradients and possibly negative values, and then you have to deal with these negative values. And so the high order schemes in SWAN, for example, they deal with these negative values by what they call renormalizing the spectra, which is a redistribution of the energy in direction space. So if they have negative energies, they just smooth it around in directions. And this is one of the reasons why the directional spectra that are coming out of SWAN in coastal areas can be pretty broad in terms of direction because it just moves stuff around. But, you have to do what you have to do. If you want to have something fast and deep, there's always some shortcuts. The other important theorem is Lac theorem, which is related to the consistency of and stability of the scheme. And in that, if you can prove that it's stable and consistent, then it can actually converge. And actually, it's very easy to make some parameterization that makes the scheme non-consistent, and then you actually never converge when the time step goes to 0. So you have to be careful about that. And then, so Aaron has been playing a lot with these ideas, and so these are typical cases of advection of. So this, imagine you have a tracer or a blob of energy, and this is a velocity field just going around like a washing machine. So your blue blob here should be turning around and remain the same. Of course, with the numerics, it's going to diffuse and do some funny things. So these are some examples. Yes, there's also some tables with the maximum values and stuff like that. What happened? But you can see the pictures. Basically, when it's white, it is because it's going over the maximum value. And when it's red here, it means that it actually has negative values. So this is after one turn with the same CSL condition using some different schemes. Okay, and you can have some stuff which is very diffusive, stuff which is less diffusive. I think this is end scheme, this is the PSI scheme, and this one is probably the, I don't remember. Yeah, some Galerkin thing. And I think the last one here is the favorite scheme of Aaron, the FCT scheme, the flux correction transport scheme, which is something like a third order scheme. Of course, it's a bit more expensive. It's like a 3 for the ejection. Yeah, and yeah, and some, yeah, so that was to give you some idea of, the spectra of the ejection can smooth things around and make it funny. And it's the same thing with the directional spectrum. So if you care about the directional resolution and distribution of the energy, this is a simple test case. This is a mesh. This is a bathymetry going from deep water to the shelf, and you have a steep slope, and the waves are coming at a very oblique angle, so they should turn a lot. And of course, when you turn a lot, you need to advect in direction space, and that can lead to some diffusion. It's more funny if instead of having a smooth bottom, you make a bumpy bottom, because then it's turning all directions, and then you'll see the effect of numerical diffusion. And that's just something I did 10 years ago. And here we are comparing first order scheme. It's a directional spreading. So the theoretical solution is that the spectrum should become narrower, so going from 15 degrees down to 4 degrees, very narrow spectrum, going from offshore to the beach. Okay, so that's the theoretical solution. It is a first order scheme. And the different symbols here are using ray tracing with different time steps. And if I was making big time step, I could get something which is pretty close to the actual theoretical solution. Aaron has been using the test case to look at the impact of schemes in SWAN or WaveWatch on the directional resolution, and you get some funny effects. In some places, you would think, okay, so here you have. All right, so the theoretical solution is red. The BSBT backward in space, backward in time. I think that's the second order SWAN scheme. This one is the FCT scheme, and this one I don't see what's written, but it's another scheme. This is using a spatial resolution of 2 kilometers, and you would think, okay, I'm going to make a finer grid, and that will converge. And no, if you make a finer grid, actually the errors can become even larger. And the reason, so it's about the same here. The blue actually is higher, the green is the same. And the reason is that it's not just about spatial resolution; it's also about spectral resolution. So you have to be consistent. If you want to converge, you need to increase both the spatial resolution and the spectral resolution to make it consistent. And in some cases, if you're integrating all the terms with the same time step, ideally you would need to have a very, very fine directional resolution to be consistent with the spatial direction. And this is one of the reasons for using a splitting approach, that you can adapt the time step to the different pieces of the equation, and typically have, in that case, a smaller error. I mean, it doesn't work better in all conditions, but in conditions like that, which are very specific, you can see the impact. Yeah. There's another, okay, so when you do splitting, you have some error, which is due to the fact that you're not solving the equation the same way. And here again, I don't know what happened to the slides. A lot of stuff disappeared. Maybe that's a PDF issue. But what you have here is a bar on the bottom with a current going opposite it, and that's the wave height. The wave height should go down to almost 0 because waves break with the opposite current. If you do the advection with many, many steps, and then you do source terms after, you have the error that the waves are, that's what's happening with the blue curve here. The waves are being advected, and then they break only after you advected them. Whereas in reality, you want to advect, break, and not advect, and then break at the end. And that's typically what's happening with the splitting method, is that you're introducing this kind of error, that you're not solving everything with the same time step at the same time. And so here, these solutions are with different time steps to show the impact of that. So that would be the good solution, and this one is errors due to the splitting error. So it's shifting the breaking patterns of that. And this is another example of waves going over bathymetry. So that's the depth here. So we have this bump on the bottom, so you have like a hill. That's the mesh of that grid. And these are the errors of the schemes compared to the very fine numerical integration with a small time step. And what you can see here on the top are the errors that are introduced by the schemes that are used in Swan, and which essentially come from the limiter. And that's the integration is not done with a time step which is small enough. And here you have errors in WaveWatch which are due to the splitting. And they can be similar, they can be smaller. It depends, how big you make a time step or not. So the different approaches have different sources of errors. And one advice I can give you is always try to run your model with reduce all the time steps and check if you have a big difference. And if you have a big difference, then maybe you need to reduce time step again. And this is for some real cases. This is depths at Swan test case, and this is the impact of the limiter using Swan on the wave heights. And so typically this is in percent, so the errors can be more than 10% on wave heights on the coast here and there. So these things do have an impact on the solution, the limiters and the integration. So always try small time steps and see what happens. All right, I'm going to skip that. It's essentially all the same story, and that's all for the numerics.